Assalamu alaikum. Hello, everyone. Today we start a new topic, exploratory data analysis. At the beginning here, there are some terminologies and some definitions. I will skip those for now. You can actually read through this yourself. I will start from the correlation analysis. So I will focus on the type of analysis that we will need towards building models for the next 3 chapters. So the correlation between any two random variables or two data attributes describes the strength and the direction of the relationship between them. Okay, it's a one number, but it can tell you two things. Okay, how strongly related these two variables to each other and the direction of that relationship. Okay, so R, the correlation here, what we focus on here for this is Pearson's R correlation. So it's between -1 and 1, and it's computed as it's shown here in this equation here. So where you have X and Y are two variables. So yeah, so here this is sum of X times Y. So it's a element-wise multiplication between X and Y. And here is sum X squared minus the sum of X all square, same for Y. Okay, the value of this is between -1 and 1. In the positive direction, okay, so as we get closer to 1, that means there is a strong correlation. There's a strong linear dependency because Pearson's R correlation is good in capturing the linear dependency. Okay, as we get closer to 1 in the positive side, then there's a strong positive relation. So as X increases, Y increases. As we move towards -1, there is also a strong relationship, but it's a negative relationship, strong negative relationship. As X increases, Y decreases. Okay, so towards the extreme cases, when X is equal, when the correlation is equal to 1, that means Y is equal to some constant time X, Cx plus some bias. And when we are close to -1, that means Y is equal to minus C times, or C, where C is negative, times X plus some constant, okay? As we get closer to the 0 from both sides, okay, the correlation is going to be less. At R equal to 0, there is no correlation at all, okay? Here, it's described here, okay? As we're moving toward 1 here, okay, the correlation gets stronger. So from 0 to 0.4, there is no correlation. From 0.4 to 6, there is some correlation. From 0.6 to 0.8, there is strong correlation. And from 0.8 to 1, there is very strong correlation. This is a positive correlation. Here, as we're moving toward -1, there is a negative correlation, okay? Here, from 0 to -0.4, there is no correlation or weak correlation. As we move very weak correlation. As we move from -0.4 to -0.6, there is some correlation. From -0.6 to -0.8, there's a strong correlation. And from -0.8 to -1, there's very strong correlation. Okay, so do I need to mention something else? Yeah, so that's it. Oh yeah, one thing, this kind of information we also can actually infer from scatter plot. Okay, if you plot a scatter plot between any two variables, if you see in average a linear pattern, okay, so as X increases, Y increases, for example, then you can infer that there is some correlation. But if the dots or the circles are all over the places, then that's an indicator that there is no correlation between these two variables, because for a given value of X, Y can take any value randomly, okay? So that is an indicator that there is no correlation between these two variables, okay? So let's work with this file here, okay? We are loading the file here, we're displaying the data. So here we have two variables, the weight and the height, okay? And here we are computing the correlation between these two. Like, given the weight, does it really tell me information about the height? Is it like as the weight increases, the height increases or not? So we can compute the Pearson's R correlation here, and we compute it and we get this value here, 0.389. So there is very weak correlation here at the edge here, almost 0.4 here, okay? So very weak, like it's between very weak and weak correlation, I would say, okay? Okay, the weight doesn't tell much about the height, I would say. Okay, and the other way around. So we can also call the function cor here inside it's a built-in, it's a pandas built-in function, and we specify the method person, and we get the value for the correlation. And here it's a matrix. Okay, this is the correlation between the weight and itself. Of course, it has to be one feature is telling you everything about itself. So the diagonal values will be ones because they are the correlation between the feature and itself. And here this is the correlation between the height and the weight, and here the correlation between the weight and the height, and they should be equal. Okay, there should be a symmetric uh, uh, matrix. So the correlation as we see here is low. Okay, I created this example to show you like the correlation here. For example, I created these three extra variables. Okay, I call them C3, C4, C5. This is equal like this is exactly equal to the height. Okay, this is equal to the 2 times the value of the height plus 5, and this is equal to 10 times the height plus 5. Okay, in all of these, each one of these variables is linearly related to the height. Okay, this is equal to the height. Okay, this is some constant times the height plus some other constant. And the same thing here is just the constant is different. So what do you expect? Like the correlation between C3 and the height, C4 and the height, C5 and the height to be. Okay, as you might have expected, all of them will be 1. Okay, okay, so here I just created them. Here I compute the correlation. Okay, so C3 and the height 1. Okay, C4 with the height 1, C5 with the height is equal to 1. So the correlation for each one of these is equal to 1 because each one of these is linearly depending on the height. So the relationship between them and the height, between each one of them and the height is linear relationship. So that's why the correlation is equal to 1. That gives you one thing you need to understand. So the correlation tells you about the relationship. Is it how linear, how like it tells you like if there is linear dependency and how strong that linear dependency is, but you cannot predict a variable from another variable by just using the correlation. So when the correlation is equal to 1, this is what I want to say. When the correlation is equal to 1, that does, for example, when the correlation between y and x is equal to 1, that doesn't mean that y is equal to x. Be careful about this. You cannot predict the value of y from x. You just know that there is a linear relationship, but you cannot predict those constants here. Okay, and you cannot say that y is equal to x. You cannot come up with that conclusion that y is equal to x. Okay, you can just come up with a conclusion that there's a linear dependency here. When the correlation is equal to 1, there is a strong linear dependency, but you don't know the value of those constants here, the slope and the bias. Okay, you cannot tell from the correlation. Okay. Another thing, so as I already mentioned, like here, if I let me do something else here. Let me do this. So to show you that now, for example, if I do this, okay, this is x squared, okay. So let me do x squared, okay. Let me do it in another, okay. Okay, let me create this here. Command V, let's call this C6, okay. And let me run this. Now this is x squared, okay? So here, C6 is equal to the height square, okay? Though this is equal, this is not, there's no linear dependency, but here we are still capturing that there is high correlation between C6 and the height. Though like the height, C6 is not linearly related to the height. This is non-linear relationship, okay? But we are still capturing that because actually all of the numbers here are positive. We are on the positive side. And still when this increases when the height increases, the other one, the variable C6 increases, okay? So somehow this is not a linear relation, but we are still capturing the like that there is a relation between these two, okay? Let's consider this example here, okay? I created this data frame here, okay? df2 here, okay? So we have negative and positive numbers. And yeah, this column is defined as x. This is our first variable. And I defined a new column y that is equal. So every element in y is equal to x squared. So this is the same relationship. It's non-linear relationship. So it's a quadratic relationship. Y is equal to x squared, okay? So now let's display this, okay? This is it, okay? This is x and this is y. Now let's compute the correlation, okay? Using Pearson's R method, okay? So when we compute the correlation here, we see like the correlation between x and y is equal to 0, okay? So which means that the correlation can actually fail to detect or to identify non-linear relationships. So you cannot really rely on correlation to identify if there is a non-linear relationship between two variables, okay? More specifically, this type of correlation we are considering here in this course. And in fact, if I plot the relationship between x and y, this is what you get, right? It's a quadratic relationship, right? This is it. So there is a relationship, okay? So by scatter plot, I can see it, but with the correlation, actually, I don't like, I get an indicator that they are uncorrelated to each other, totally uncorrelated. There is no correlation here, 0. But actually, there is a relationship here between these two. So that's why a scatter plot is sometimes important, okay? So you use correlation to detect if there is any linear relationship. If you fail to detect any linear relationship, then you may plot the scatter plot to see if there is some kind of nonlinear relationship between these two variables, okay? Now we come to another interesting topic, which is principal component analysis. It's a dimensionality reduction technique, okay? It's good like if you have so many features, some of them are maybe okay, let's talk about in the context like of, you have so many features, okay? Many of them are very correlated to each other. Okay, then there is a room here for dimensionality reduction. Okay, your data points are in the n-dimensional space, wherein is the total number of features, but actually they live in much smaller space. Then you can project into a lower space. Okay, so you remove any redundancy there. Okay, so you're with the much less number of columns, you are still representing the same data. You're not losing much in the data. This is useful. For example, if you have one variable that you wanna predict from a set of input features, then maybe many of them are correlated to each other, okay? And some of them are weakly correlated actually to the target variable. You can actually do this dimensionality reduction in order to actually reduce the number of them. Oh, in fact, the ones that are not correlated, you remove them manually. That are not correlated to the target variable, you can remove them manually. But dimensionality reduction is good when there are many are correlated to each other. If there are many are correlated to each other, then there is a room of dimensionality reduction here, because it's good if every feature is telling you something different. You don't want redundancy here. If they are very correlated to each other, then there is so much redundancy here. So when it comes like to input features, you need every feature to tell you something different. Okay, you don't want that redundancy. So if there is a redundancy, and in fact, reducing the number of features is very useful for in many cases is very useful for your learning process, because as the number of features increases, the number of samples you need to train a model increases exponentially. So as the number of features increases, you are complicating the learning process. So if you have a very limited number of samples and many features, then you may run into the problem of overfitting. Okay, you want to avoid that. You don't want to fit every training sample. Okay, you want to generalize very well outside of your training data. So that's why maybe sometimes we do it with adding regularization term in the learning process, or by using principal component analysis. In the regularization, we are actually killing some features, or bringing the features, the weights of some features to be 0, but we are left off with some of the input features. But in principal component analysis, we are actually moving totally to a new set of features. Okay, they are representative of the original ones, but in much lower dimensional space. So let me explain this here. Okay, so let's look at this video here. Here we have these data points. Okay, now these data points, every one of them is represented by two coordinates, x and y. Okay, so each one of them lives in the 2D space. Okay, so if I want to actually project it into 1D space, okay, then which coordinate should I come up with? Okay, so deciding the coordinate is very important here. You want the coordinate that actually maintains doesn't like reduce the distance between the points that much. Okay, so you want the one that maximizes the distance between these two after the projection. Okay, that's the one you will choose. We will see why. Okay, let's assume these points here and let's project them in x and y and see how much we lose in the distance between the points. Okay, so here we projected them in x. Okay, we projected them in x. As you can see, these 2 points became 1 point. We lost any distance between them because actually we totally excluded the y component. So here the unit vector. So when you project, you multiply with the unit vector, right? U transpose times your vector, right? So here, if you want to project into the x coordinate, then y has to be 0, right? If y 0, then x needs to be 1. That's the vector you multiply with by multiplying with this vector, you are projecting in the x coordinate, which means you are killing the y component. So now you're moving from 2D to 1D. Always moving from higher dimension space to a lower dimension space will lead to error. Okay, the projected point is not as the same as the actual point. Okay, there's always error, but how much error you run into versus how much you benefit in terms of like performance of your training algorithm, that is something, there's a trade-off here. You lose something, but for something. Okay, so in like the bottom line here, the dimensionality reduction will always introduce an error. Okay, and you want actually the goal here, we want to find, okay, let me go one step at a time. So here, as I said, when we project into x, these 2 points, we lost any distance between them. Okay, and this is the range here. Okay, this is the first point and the second point, and it's also an indicator of the variance. Okay, this is the variance. Okay, let's say variance for now. Okay, okay, that range, it's the range, but let's refer to it as the variance. Okay, this is the variance we achieve here. Okay, when we project into x, let's see, and we lost the distance between these 2 points and these 2 points. Okay, totally. Okay, they are projecting to the same point on the x-axis. Now let's look into the projection on y-axis. Okay, so it's here. Okay, so this is the projection on y-axis. So we are left off with 3 points only because these 2 points project to the same point. So we are losing any distance between these two because we are excluding the x component. Okay, so we are using only 1D, one line, one coordinate, which is y coordinate here. So these are projected into 1 point. These are projected also into 1 point. And this is the variance here. Okay, now let's look in this direction here. Okay, it's gonna come here, this direction here. Okay, so as you can see here, projection into this, I still like I preserve the distance much better than here and here. Okay, so each point is projected to a different point, and the distances are they are not as they used to be here, but much better than projecting into y and x. Okay, so these are the points. Okay, and I maintain like every point separate, so they are not colliding, and there is some distance between them. Not the same distance we used to have here. Okay, but not too bad compared to projecting into y and x. Okay, so this direction has higher variance, as you can see here. Okay, higher range. Okay, so then we can come up to a conclusion like the direction where the variance after the projection, the variance of the projected points is maximized, is the best direction to project to. Okay, so we are moving from 2D to 1D now. We are considering only one coordinate, which is this one. If I want to move from 2D to 1D, then I need to choose the direction where the variance is maximized, the variance of the projected points. Okay, that's the best direction. Okay, that's identified by a unit vector U1 and U2, and that's the vector we want to find. Now, if I choose this as the first direction, then what will be the best second direction to choose? Okay, because now this is if I want to go back to 2D. Okay, so then if I have chosen this as my first principal component, okay, we call them principal component. If I choose this, okay, this direction, this to be the direction of my first principal component, then what will be the direction of the second principal component? The second principal component first has to be orthogonal to the first one, and among all orthogonal directions to the first one, the one that captures the high, like the more variance is the best one, of course, after this one. So one direction is this one, and the other direction is the one that goes into through the screen, right? Z-axis, right? But in Z-axis, there are no points here. All of the points we have are in the screen, on the surface of the screen. So they have their Z value is 0. Therefore, there's no variance in Z axis. It's 0. But there is variance in this action in this axis. Okay, it's not 0. Okay, so then it's the second best direction is this direction. Okay, the one that's orthogonal to this one. But now, if we choose these two principal components, actually, what we did, we went back to 2D. Okay, we have just rotated the coordinates. Okay, we are back to 2D. We didn't compress. Okay, so this is just for the sake of the explanation, because what I want to say, the maximum number of principal components, is equal to at most, assuming like the number of features is always less than the number of samples, then the maximum number of principal components is equal to the number of features. Okay, to be precise, is equal to the min of the number of features, the minimum of the number of features, and number of samples. But let's assume like the number of samples will always be greater than the number of features. Then the maximum number of principal components you can have is equal to the number of features. But if you go back, if you consider all these principal components, okay, if you consider n principal components, then actually you didn't compress, you compressed nothing. You went back to the same space. You just rotated the coordinates, okay? So in practice, actually, if, for example, if I have 100 features, my points are in 100D, we want to compress them to go like to a number of principal components that capture, for example, 97% of the variance. That could be only the first 5 principal components or first 10 principal components. And maybe sometimes you get so surprised, maybe the first 2 principal components can capture 97 or 98% of the variance. There are so many correlated features, we don't really need to work with all of these features. We can just work with only the 2 new features, the 2 principal components. And for example, assuming like there are 2, okay? These 2 are like capturing like most of the variance. And if you plot the scatter plot between these 2 principal components, you see like they are uncorrelated. If you plot the scatter plot, you will not see any pattern, because everyone is telling you something different. Okay, there's no redundancy between them. Okay, so yeah, I have waved so much and tried to explain things visually, but hopefully the idea is clear. Okay, and this is what we are saying here. Okay, so you can read through the text here. Like we are choosing the unit vector u that maximizes the variance for the projected points. Okay, so U transpose xi is the projected version of xi. Okay, it's the projection of xi into the direction that identified by the unit vector u, and this is U transpose x bar. This is the average after the projection. As I said, this is the variance after the projection. Okay, so this is the variance. This one. So yeah, this is okay. So why it's not here? It's the variance after the projection. So we want U that maximizes the variance after the projection. Okay, and we're not gonna go into the details of how to solve this optimization problem for this course, but there's a way to solve it. Okay, that's it. So here just is another representation of the same problem. U transpose SU, where S is equal to this. These are both the same thing here. Okay. Yeah. So here, as I said, we find the first vector that maximizes this. Here it turns out to be this one. Okay, this direction. Okay, so we want to find the unit vector u that identify this direction, and then Yeah, that will be the first BC. Find next BC unit vector orthogonal to previously found BCs with which maximizes this. So the second one that maximizes this, it has to be orthogonal to the first one that we found. Among all orthogonal directions to that one, we choose the one where the variance is maximized. And we keep repeating this so we can come up with a number of principal components as much as the total number of features. But in general, we want to only keep like very few of them. Okay, if the features are many of them are correlated, then actually we can actually compress a lot. Okay, so with that, I will stop here for today. Next time we will start with the first case study, inshallah. Thanks for watching. Assalamu alaikum.